So I wrote down to number 28 here. Not that you had a question on this probably, but I just wanted to point out some things. Our lesson today in the book is just about functions, function notation. Everything we do in calculus is wrapped around functions. It's dealing with functions. So ideas like domain and range and those kind of things are important to us, and function notation. So the first quiz, a lot of it is going to be about notation. Most of it should be review kinds of things as we get into these chapters, but it's going to, I'm picking out the things that you've learned in the past about functions that are going to be important for us this year. That's the key. And we may look at some of these things a little differently than you had in the past. So even though it might be kind of review, it's still looking at some things maybe in a little different way and so forth. We really won't get started with calculus stuff other than what we did with our kind of big ideas with slope and area and that kind of stuff, really until section 4, which is after our first quiz, right? Our first quiz will be next Thursday, by the way. And so we're talking a lot about functions here and all year long. So this was the function you were given, g of x. And we talk about domain and range. We talk about x and y usually. You won't hear me talk about x and y so much as I'm going to say input and output, right? Input and output. So every function, I mean, that's what a function is, right? It's a function. A function is some rule that assigns an input to how many outputs? One and only one output, right? So any input can only have one output. That's the old vertical line test, right? You can't put something in and get out two outputs, right, to be a function. So you put in, for any input, you get out only one output, okay? So x is our input here, and then g of x is our output. So g of x is like the y, okay? Now, when you first in algebra learn about graphs and things like that, you would look at this as a point, right? -1, 5, you'd look at that as an x and a y. I'm going to call that an input and output. Put in -1, get out a 5. Now, one of the problems is we also use that as interval notation, right? I mean, that means the interval from -1 to 5. So when we talk about points on a graph in calculus, points on a function, we're going to usually write it like this, because doesn't that say the same thing? Isn't that a point, right? So when I say, hey, what did they give you here? You're going to say, well, they gave you 1 point on the G graph. That's 1 point on the G graph. -1 in, 5 out, right? That is a point that they give you. So when we write an ordered pair, we won't write them this way very often. We'll write them this way most of the time, okay? All right, so anyway, what does that mean? Well, that means you're going to put a -1 right here for x, and you're going to put a 5 over here for the g. And so you got 5 here, you got this here. Now, if we want to solve that for a, we can divide. It would look like this. I would be fine if you leave your answer like this. I'm guessing most of you didn't. We could take that negative power and flip it up to the top. One of the things I think I said to this class yesterday is you should try to do problems without your calculator as much as possible until it becomes necessary to use your calculator. Now, if you look up in my solutions manual here, this is the answer they have. Now, how many of you have 6 point something? Raise your hand for number 28. Is that what it is? Does it come out 6 point something? No? What is 20? Did we do 28? What do you get? You just left it like that? Good. Okay, good. The other class, the vast majority of people typed in their calculator, got a decimal, 6, I think it's 6 point something. Did anybody do that? You did? Okay. Which is fine. You can do that. Now remember, we said 3 decimal places, right? So again, the rule is if you give a decimal answer, it has to be accurate out to 3 decimal places. But why not just leave it like this? This is fine. I actually don't mind this. Mrs. Andreessen would never let you leave a negative power in your answer. But move that up to there, and that's fine. But it's good. I mean, you got to learn that. How do you move those things around? Because sometimes you want to do that. But in this case, either one of those is fine. It's just rearranging. Decimal answer would be fine too. Okay, so I just want to talk about that. Okay, the next one I have up here is 52. Does anybody have one they want to see before number 52? okay? And we did a lot of this in that IXL, so maybe that's answered a lot of your questions. Okay, I want to talk about this one right here on 52. We talked a little bit about this yesterday about, or maybe it was 2 days ago, about rearranging these things. So they gave you this, and then they asked you for this. So I would probably just, well, let's see. One way to do this would be raise that 4 to the 2.1, and that equals A. Would that be reasonable to do? Okay, and then what we're looking for, I guess maybe I could call that x over here is what I'm looking for. So 2 raised to the x is equal to a. Maybe that'd be a good way to do that one. Okay, now I look at these two, and they both equal a. So 2 raised to the x would equal 4 raised to the 2.1. How can I make those equal? Make that 4 into 2 squared, right? And what do you do when you have a power on a power? Multiply. And so x would be 4.2. That'd be one way to do it. Anybody do something different there? You may have a different idea. I just thought of this last block. Just while I was doing this, I thought, oh, you know what we could do? I talked about that change of base the other day. I could do this. We're trying to find x now, right? We're trying to find x. So x would equal ln A over ln2. Would that not be a true statement? Remember that change of base thing we talked about? You can take any log, and then you can do any other log of this divided by that, right? So ln's a good one to do. That's what we work with all the time. So ln A over ln2. And then I could do that over here, too. I could say, well, ln A over ln4 is equal to 2.1, right? So I can just do that on that side. And then I could multiply this ln2 over here, so I have x times ln2 would equal ln A. And then ln A would also equal 2.1 times ln4. Would you agree with that? So 2.1 times ln4 would equal ln A, and x times ln2 would equal ln A, so those two would have to be equal to each other. And we talked about this yesterday. What's another way to write ln4? ln of 2 squared, right? And then what can you do with that 2? Bring it down in front. So now we'd have 2.1 times 2 ln2, and 2.1 times 2 is 4.2 ln2. And over here you'd have x ln2. And so look at that, x ln2 divided by ln2 on both sides, you get x equals 4.2. So that kind of came to me. It just using the different log properties, right? And so as long as you do something that's legal, you've got a variety of different ways you can think about those. So it's just good to see those different things there. Okay. All right. What else? I've got, I want to make a comment. 45 is not one we had to do, but I want to make a comment here. Natural log and e are inverse functions, very much like square root and square, right? You square root 3 squared, you get 3. They kind of undo each other, inverse functions. So what's e to the ln x? What's e to the ln x equal? X. This equals x, right? It's like the square root of x squared. It equals x, okay? Inverse functions do that. Now, there could be some domain issues. There would be with square root, but we won't get into that right now. But e to the ln x is just x, okay? Likewise, ln of e to the x is just x, right? Now, that one's a little easier to realize because we know we can bring that x down in front, and we do that. And then what did we say yesterday? ln e is what? What's ln e? 1. ln 1 is 0, and ln e is 1. ln 1 is 0, ln e is 1. Okay, so ln e is 1, so this is just x. So ln e to the x is just x, e to the ln x is just x. They're inverse functions, they undo each other. So whenever I see something like this, it makes me think, oh gosh, that's close. That's almost an e to the ln kind of thing. So what we can do is in reverse. What can we do with this too? Put it in the parentheses, right? So we could turn this into e to the ln x squared, and then what is that going to equal? That's going to be just x squared, right? So that's something that can be kind of again, I've seen that happen on those multiple choice questions. also, where you work it all out, it's got exponentials and logs, and you get down to this point, and you have this, and then the answers, it doesn't have that, but it has x squared. Well, that's because this is the same as that, right? But it's just using those properties. Okay, so those can come in handy at various times. So that's not one we had to do, but I threw that in. Okay, 58, 62, 64, any, you want to see any of those, all those? What do you think? I just wrote those up because I thought sometimes those are ones we have questions on. 64 for sure. Okay. So, well, let's do that. I'll just talk through 62. 62 is a little easier version of 64 because what we have is one unknown. We have this k that we don't know. So one of the reasons we worry about exponentials and logs, I think, is number one, those seem to be functions that people just struggle with for whatever reason. Log ones especially when they first learn about it. And then the other thing is in calculus, one of the big topics, or one of the topics we talk about is something called differential equations. And, if you go into engineering or something like that, and you get done with calculus, the next class you take, math class after calculus, is differential equations, okay? And we're going to learn about that a little bit, but one of the more famous and one of the more useful differential equation, basic differential equations you learn about are exponential growth and decay. Okay, so solving exponential growth and decay problems are kind of an important concept when it comes to differential equations. So when we have a situation like this, we have an unknown. Well, what we have here is what's called an initial condition. So we have an unknown value in this function, but they told us one of the values of that function, so that allows us to find that unknown. So what do? Just like we were saying, we put our 10 in for the h, we put our 1 in for the x, and we end up with this. We divide both sides by 20, we get this. Now I did the ln of both sides, but you could just go right to log form. The log base e of 1/2 is equal to k. We can just turn this right into log form. This is your base right here. Okay, e to the k equals 1/2. But I just did the ln of both sides, and now we can bring that k down. But we just talked about that. What's ln e to the k? Ln e to the k is just k. Ln e to the k is just k. And then we get ln 1/2 and just leave it like that. Okay? Although ln 1/2 is very often written this way. Ln 1/2 would be ln 2 to the -1, and then you can bring that -1 down in front. Ln 1/2 is very often written negative ln 2. Okay, just to get fractions out of there. But again, that's one of those things we want to be ready for. Okay, let's talk about 64. So in 64, the difference is, and this is very common in differential equations, is we have two unknowns. We have two unknowns. So the way we find two unknowns is we need two values that can help us find those unknowns. Okay, so this time we have a j function, and we know two of the values of the j function. So what we do is we put both of those into the function. So we put a 5 in for j and a 1 in for x, and that gives us this. And then we put a 10 in for j and a 3 in for x, and that gives us this. And what do you do when you have two equations with two unknowns? An old algebra thing. Set them equal to, solve for one of the variables and set them equal to each other. Substitution, essentially, right? That would be another thing to do. Solve one of them for one of the variables and substitute it into the other one. That's what we do with two equations, two unknowns. So now, in this case, I went ahead and solved both of them. So I divided by e to the k here, divided by e to the 3k, so they're both equal to a. So then I just did that. Okay? So now those two are equal to each other. So now I've got the a out of there, now I just have one variable. Now the other thing I could have done is I could have taken this, and stuck it right in there. So I'd have had 10 equals 5 over e to the k times e to the 3k. Right, so I could have done that. Then I could have divided the 5 over to this side. I could have put the e to the 3k there. Right, I could have done that. Right, and that's what I'll do right here. Right, I could cross multiply these right here. So I'd have 5e to the 3k equals 10e to the k, and then do the same thing. Divide this 5 over to this side, and divide this e to the k over to this side. Right, either way, I end up with that right there. Right? What can I do with that then? What can I do in this side? going to do when I'm dividing and the bases are the same? Subtract the powers, right? And subtract those powers. Okay? So when I get to this point right here, I can just subtract those powers. 3k take away 1k. Okay? And now I can just go to my log form, or I can do the ln. I prefer ln on both sides for whatever reason, I don't know. But ln on both sides. What's ln e to the 2k? 2k, right? That's just 2k. And then divide by 2. Now, you'll notice that I don't divide a lot. If I say divide by 2, I end up writing it as a 1/2, and you'll find out as we go through the year, it's a lot nicer to have even if it's a fraction, it's a lot nicer to have a coefficient in front of something than it is to have something divided by something. That just gets messier. So it's better, instead of putting ln 2 over 2, which is fine, you can do it, but there's going to be times where it's just nicer to have it written 1/2 ln 2. Okay? All right. Now we're not done though, right? What else do we need to do? We got to find a, right? Now one of the things we had was a was equal to 5 over e to the k. Was that right? That was one of our a's. There was another one, but that was one of them we had. So now we got to put that into there. So we just go a equals 5 over e to the 1/2 ln 2. Now I would be okay for a final answer. I'd be okay leaving it that way. That's fine. Okay? But the reason we need to know about simplifying things is because sometimes we're not stopping there. Sometimes we want to take that and put it into something else. And having it in a simpler form will make life easier. So another version of this we could have done. We could have taken that 1/2 and stuck it inside there. Why would I want to do that? Because I see that e and ln thing, and I know those things cancel each other, so I know that's good. So what would we have if we put that 1/2 in there? What's 2 to the 1/2? Square root of 2. What's e to the ln square root of 2? Just square root of 2, right? And again, Mrs. Andreessen would probably not let you leave it like that, so let's multiply radical 2 top and bottom. You get 5 radical 2 over 2. But for this particular problem, I would take any one of those. Any one of those are okay. They're all the same. Okay, they're all the same. You got k and you got a. All right, and so that's, again, not something we're going to do on next week's quiz, okay, but down the road, as we get into stuff, it'll be expected you have to do it. It's not going to be in this quiz, but this is going to come up. It's going to come up, and we'll want to be able to handle it, okay? So we'll see it routinely from time to time, and we'll get better at it as we go. All right, and then I'd just comment on 66. This just shows if you have some other stuff up in the power, doesn't matter, do the ln on both sides, and then you can bring the x plus 3 down. ln e is just 1, and then subtract 3. You know, it just, not a big deal. All right, let's go over to the story problems. Maybe look at number 2, just talk about number 2 real quick. There's a lot of language here in these story problems that I want to make sure that we're getting, and some of you struggled with this, I could tell as I went around and looked at this, and it's normal. I mean, probably the hardest thing we do all year long is the section where we have to do some story problems, and we have to draw some pictures, and we have to set up functions, but it's like one quiz that we do all year long that really has a lot of that in it, okay? So it's natural. It's natural to struggle with this. But some of the language, they said in this one they had a cube, okay? We had a cube that was 10 on a side. Okay, so we got this cube. 10, 10, 10. It's got what? Water in it? Is that right? This thing filled with water, is that right? Okay. Okay, so we got, all right, so we got this cube. So we got some water in it. And it's D is how deep the water is. Right? I didn't see a lot of pictures on this one either. See, to me, the first thing I want to do is a picture. Now, it says, express the volume as a function of the depth. What does that mean? What are they wanting to see on your paper? V equals. Yes, as soon as I read that. Yes, and this is what I'd like all of you to get to. This is the language of functions. When they say write the volume as a function of depth, it would please me greatly if all of you would then, right away, when you read that sentence, write that on your paper. Okay? That's what they're saying. They're saying D is the input, and they're saying V is the output. V as a function of D. Okay? Okay, so that's just volume. What's the volume of the blue? It's a box. 10 times 10 times D, right? Not 10 times 10 times 10. We don't want the volume of the box. We want the volume of the water. 10 times 10 times D, 100 D. That's it. That's it. Volume as a function of depth means they want V equals with some D's in it. That's what they want. That's what it means. Okay? Now, they also talk about domain and range. Did they talk about domain and range or just domain? Domain and range. Okay, that's important. That's important on functions. Now, what is domain? What is domain? The possible X values, the possible inputs. The possible inputs. Now, we say possible inputs. What we really mean are the inputs that would have outputs. That's what we really mean. The possible inputs are the inputs that would have outputs, okay, in this problem. So what would be the smallest, I usually think of it, what's the smallest D can be, what's the biggest D can be, and is there any numbers in between there that it can't be, right? But what's the smallest D can be? 0. Biggest? 10, if it's full. So D could be 0, it'd be empty. D can be 10, it'd be full, it could be everything in between, and it can't be anything else. D can't be 11, right? There you go. What's the range? Well, that'd be the possible outputs, which in this case are volumes. Well, that'd be 0 and 1,000. Okay? Domain and range. And then finally it said, right, D is a function of V. So that means just solve this for D. So D would equal 100 over V. But it would be nice to say D of V. That would be good notation. But so, again, big thing is just the notation kind of stuff. All right, let's talk about 4. And we're foreshadowing here a little bit. We're foreshadowing because one of the big calculus things that we do, one of the big applications of calculus is in business is profit and cost kinds of things. Okay, when you're a business major and you take an applied business calculus, most of the problems you do, what you're working on, are these kind of problems. Okay, so we have a situation where we can make these mugs, we can sell them for $1. They cost us 60 cents to make, so we're going to make 40 cents on every mug. But if we lower the price, we'll sell more. So that's a dilemma. Selling more, that's good. Lowering the price, that's bad. Right? So how much do we lower the price? Pretty soon we lower it too much and we're not making any money. We lower it, right? We don't lower it and we don't sell enough, right? And so where is that at? That's where the calculus comes in. But we can't do the calculus to it if we can't write the equation for the profit. So we're trying to find an equation for the profit. Well, the profit would be however many mugs we sell times how much profit we get on each mug. Right? So they already wrote the equations for you. They just asked you to explain. So just very quickly, we can sell 1,000 mugs. Oops, that's a mistake. That's not a 5. It's a 50. Okay. We can sell 1,000 mugs, and then they also tell you let X be the number of price reductions. So every time we reduce the price a penny, we sell 50 more mugs. So the number of mugs is going to be 1,000 plus 50X, right? X times X is the number of reductions. Then we get 50 more for every one. The profit per mug is we're going to make, it's $1 minus 60 is our profit. That's 40 cents. But we're going to lower our price for every price reduction. So we're going to sell them for $1 minus a penny for every price reduction. So that's where this comes from. So X is number, so 2 price reductions, we'll take off 2 cents. 3 price reductions, take off 3 cents. So this is how much we're going to sell them for minus the 60 that it costs us. That's our profit on each mug. So what is our profit equation then? Big P. What do we do with these? We just take that one times that one. That's all you had to do on that, right? The profit then, the total profit is just going to be this one times this one. This one times this one. Number of mugs times the profit. And then they said you could go ahead and graph it and figure it out. So what happens? You get this, and where are you looking? You want to know right there. And that's where the calculus is going to come in. We're going to use calculus. Once we have this equation, we're going to use calculus to find that spot, that max. Okay? Now, you could just graph and find it. And what was it? It was X was 10, I think. X was 10, which means what? 90 cents we're going to sell them for. So if we sell them for 90, that's going to be our best scenario, right? We sell fewer than that, we're not selling enough to maximize our profit. We reduce the price too much, then our profit goes down. So that's kind of the sweet spot right there, okay? One of the big applications of calculus is finding that spot right there. All right, let's jump to number 20. We'll come back to number 11. I like to do number 20 because it's a nice strategy for using. How many people are in chemistry? Okay, been in chemistry. In chemistry, don't you do that a lot with units where you try to dimensional analysis? Is that what it's called? Or where you try to get units to cancel kind of thing. Well, here we're going to rent this limousine, and we got two things going on. We're going to pay for the gas, and we're going to pay for the driving. So what I did is I had all these things with units. So what I like to do is just write them down, and then I know I want my final answer to be dollars per mile. And they said write your cost as a function of V, the speed. So I wrote down C of V right away. But I know they want it to be cost per mile. So I know that's what I want to end up with. So a great strategy then for setting these up is just make the units work. Just make the units work. So I know I want dollars on top. So when I look at the gas, I see $1.50 a gallon. So I want dollars on top. So I'm going to put $1.50 on top per gallon. And then I need to get dollars per mile. So that means I don't want gallons in there. So I need gallons to go away. And I need miles to be down here, right? And then gallons will cancel. And I'm going to end up with dollars per mile. So how can I get gallons over miles? Flip it, right? So this is miles over gallons. So let's flip it. So 7. And then this would be 180 minus 2V. And that would give me, so right there, that would give me dollars per mile. So I just think it's a nice strategy. Plus, now we got the driver we got to pay. And again, I know I want dollars on top. So I got $15 for 1 hour. And so I need hours to cancel. And I want miles on the bottom, right? Because I want dollars per mile. So I want hours to cancel. And so hours per mile, well, this is miles per hour. So I need to flip it. So 1 over V. Right? And that'll do it. So now 150 times 7, that's 1050 over 180 minus 2V plus 15 over V. That should do it. So V is my input. So everything was in terms of V. So V is my input, which is what I wanted. And I know that this is going to add up to dollars per mile. So it's just a nice strategy in some stored problems. It can be helpful. Okay, make the units work. All right, number 11. Now, this is, again, they say you got this snowmobiler stranded in the snow. He wants to get to this service station. Now, I don't know, some of your pictures I saw, I'm not sure you were quite understanding the wording of it. It says that he's 3 miles due south of the road and is 6 miles east of his position. So his position would be straight up to the road and then 6 miles east. And so that's what we're looking at. That's the situation. So the dilemma here, again, this is very much like the mug problem. The dilemma is, where's he going to go to get there the fastest, really, right? I mean, that's the dilemma. He wants to get out of the snow and get out of the cold, and he wants to get to the service station. So what would be the advantage of going straight up to the road? You can walk faster on the road. Disadvantage, of course, it's farther, right? It's farther. So that's a disadvantage, right? Or he could walk directly to the service station, but it's in the snow. He walks slower in the snow, right? But shorter. So there's this dilemma, right? There's this dilemma. So, and then he could do somewhere in between, right? He could walk somewhere in between, right? Get there the fastest. Now, the silliness of the problem is while he's sitting there calculating all this, he's, freezing. So he's going to sit there and he's going to make these calculations. I know he's just going to get up and go, but whatever. But that's the idea. The idea is if we can figure out how long, right? What's that maximum? What's that best place that he should go to get there the quickest, right? That's what the calculus will do for us. But we can't do the calculus if we can't set up the equation for the time. Okay. So they want us to write the time it takes him to get there as a function of r. which is the distance he walks on the road. So that means that this would be R right here, right? R would be the distance he walks on the road. Now, he might go straight up, then what would R be? 6. He might go straight to the service station, what would R be? 0. Or R could be something in between, right? Well, we just found our domain, didn't we? They didn't ask for it, but wouldn't that be the domain here? And why do you want the domain? Well, sometimes you want the domain so you can set your window. Maybe if once you get this, you want to graph it. So knowing what window to set would be good. Well, that would be your window, right? That would be your domain. Those are the possible values of R. R could be he doesn't walk on the road at all, or he goes a distance of 6. All right. Also, what are some other things we need to know here? Distance is equal to rate times time, right? And we're wanting to do time. So time is going to be distance divided by rate. Oh, but we know his rate. We know his rate on the road is what? 4. And his rate on the snow is 3. So if we add up his snow time plus his road time, and time is distance divided by rate, so this is going to be something plus something, right? So distance divided by rate, we know his road time is 4, and we know his snow time is 3, so we already know those rates. So that was easy. And we need distance. What's his distance? What's his road distance? R. His road distance is R, right? That's what we defined R to be, is his road distance, right? So this should be time, right? This is distance divided by rate. Distance divided by rate. Now we need his snow distance. That's this right here. Right? How do we get that? Well, we got a triangle here. We do Pythagorean theorem, right? Problem is, what is this right here? Wouldn't that be 6 minus R right there? If this is R, this would be 6 minus R. So wouldn't this be the square root of 3 squared plus 6 minus R squared? Wouldn't that be Pythagorean theorem on that right there? Be this squared plus this squared. Now if R is 6, if he's going to walk on the whole road, then 6 minus 6 is 0. That'd be gone. Square root of 9 is 3, so his snow distance would be 3. And if his R is 0, if he doesn't walk on the road at all, it'd just be a regular Pythagorean theorem. But that'd be it, right? Wouldn't that be the distance? So that just goes right here. We don't need to simplify that or anything. There it is. Right? There it is. So now we have an equation. We have a function for his time. And we know it's time because time is distance divided by rate. That's his distance on the road, his rate on the road. This is his distance in the snow. This is his rate in the snow. Add those together, that's his total time. Now we could bring in some calculus. Now you could graph this, and it probably, you know, the mug problem, we were looking for this peak. This would probably be a situation where we have a graph that probably does that. We'd be looking for that, right? We'd be looking for that low spot where the time is the least, and that's what he should do. That would be the R value. That's how far he should aim to walk on the road. Now again, it's kind of a silly problem. As far as being realistic. But here would be a similar problem. Here would be a similar problem. You have a river. You got a power lines on this side. You got a house over here, and you want to get, or a business or whatever, and you want to get power across here. So you can go over top or you can go underground. But it probably costs more to go over the river, longer distance, probably harder to put up the cable and so forth. As opposed to going along the bank and then across, a shorter distance here. Or maybe you do something in between, right? So an engineer or somebody like that would be figuring out these costs. Should I go straight there? Should we go here and then there? Or should we do something in between? It'd be a very similar problem. Very similar problem. Would be the minimum cost. Okay? So, same kind of situation. All right. Let's open up your books to page 1. Page 1. All right, so now I told you that we kind of jumped around a little bit with some things, but now we're kind of zeroing in on this first quiz that we're going to take, and it's going to be a lot about just function notation and graphing and graphs. So what are you going to have to do? You're going to have, of the stuff we've done so far, you know, the area and slope stuff, that's kind of big picture stuff. That's not really on this next quiz, but being able to graph on your calculator. So this first quiz is a lot about functions, okay? So being able to graph a function on your calculator, be able to trace, find some points, know what they are in context to some problem, like we did the other day with the elevator and her speed in the rocket and how fast she was traveling at certain times and so forth, be able to trace and understand what those things mean. Okay, so you're going to have to be able to do that. So the things we've done so far, that's one thing to be on this next quiz. Okay, graph, and be able to use your calculator in that way. So if you have questions about the calculator, if you're uncomfortable with it, come see me. I'll help you with that. Okay. And then the stuff we do in our homework now going forward, right? And of course, all this stuff with exponentials and stuff, whatever, that may show up. I mean, something about that, simple, whatever, things we should know. I mean, that may show up, but that's not a big emphasis. I'm not going to give you just problems like today's homework at Appendix E. I'm not just going to give you exponential problems to solve. That was last year, okay? But something may come up in the course of a problem where you may need to, something like that. All right. So if you on page 1, bottom of page 1, read that little paragraph there where it says example 1. All right, so turn the page and you have these two graphs. So we have a balloon. We have this balloon in the Kansas prairie, and we have these two graphs. Okay, so look at the units on the graphs. Look at the units on those two graphs. And now close your eyes just a second and just picture this balloon. Okay, just picture the movement of this balloon. Now, how many of you pictured a balloon just going up and down? Raise your hand. How many of you pictured a balloon going across the prairie? Up? Okay. And we usually do, right? And typically that's what most people do. Now, look again at the information in these two graphs. Could it be just a balloon going up and down? Right? Because what is this one giving us? Just how high it is off the ground at a certain time, right? And this one is vertical velocity. Very important that they said vertical velocity, because if it's going diagonally, right, like this, right, then it's got this speed, and if you've been in physics, you know there's a horizontal and vertical component, so this speed is different than its up and down speed, right? I mean, if it's going almost straight across but a little up, it's just got a tiny bit of vertical velocity, but mostly horizontal velocity, right? So you run into two dimensions here. So it's important to understand we're just single line motion, right? So we're just talking up and down. So we're just looking at how fast it's going up and down. So it could be going across like this, but we'd only be focused on the up and down speed. All right, anyway. So understand what the units are. So one of the things you need to be able to do on this next quiz, very simple stuff, is you got to be able to read. If I give you that point right there, Vanessa, what would that tell you about the balloon at that point right there?
That it's probably 6,000.
At? There you go. Now, maybe they would tell us that this started at noon. If they did, then we would say at 12:01, the balloon was almost 6,000 feet high. It was 5,800 feet high, whatever. You'd be estimating, right? So be able to read off of a graph and understand and use the units and be able to maybe say what that was showing, okay? And then what would this point right here tell us? Max Rademacher, what would that point tell us right there?
At 1 minute, its speed was decreasing somewhere between 1,000 and 0.
Is it true what he said that the speed is decreasing at 1 minute? that true? I wasn't, you went farther with this than I was thinking of. Isn't that true? Yeah, because this is at speed. Well, now we got to be careful with speed and velocity. What's the difference between speed and velocity? Somebody help us out with that? Physical science people? Physics? Didn't you talk about this in physical science freshman year? Maybe not, I don't know. Velocity includes direction. Speed is always positive, right? Speed is always positive, okay? Velocity includes direction, so it's positive and negative. Notice how down here it's negative, right? We would never say the speed is negative, so we got to be careful. Velocity. So the velocity is decreasing because the graph's doing what? It's going down. But here's why we got to be careful. So right through here, isn't the graph also going down? Right? So the velocity is decreasing. Now I'm getting a little bit ahead. I'm getting into something we're going to talk about in section 4 later. But right here, the velocity is decreasing, right? This graph's going down. But what's the speed doing? Isn't the speed increasing? Think about what the speed's doing. This thing's like 500 feet per minute, then 600 feet per minute, then 700 feet per minute, then 800 feet per minute. Down here, it's 1,000 feet per minute. Isn't it getting faster? But it's going down, right? The balloon's going down. So here's what I was looking. Well, somebody else tell me. What else does this point tell me? And I really only care, Max, about this point, not the fact that it is on the graph where it's going down. So you're right. The speed was decreasing. It is decreasing there. But what does just that point tell me about the balloon? At 1 minute, it's... Well, and you said it's going up, but you guys are getting more caught up in the direction than I want you to, but that is true. It is going up, right? Because this velocity is positive, so the balloon is going up. That's true, right? Which seems weird because this graph's going down, but remember, this is velocity, not the direction of the balloon. But I guess you're missing it. At 1 minute, the balloon's velocity is 800. That's what I was getting at. That's what I was getting at. See, like here, Vanessa just said at 1 minute it was 5,800 feet high, right? You just read the point. That's what I was getting at. At 1 minute, the balloon has a velocity of 800 feet per minute, right? So you got a little too caught up in some other stuff, which was true, and it's good to think about, but it's more than you needed to say. At 1 minute, the balloon is going 800 feet per minute. Now, since it's positive, it is going up, right? Because notice that, doesn't that point correspond to this point over here? And this point is going up. Okay. Now, the red points here are interesting to me. A little past 1, we just talked about the bugs and the peaks, right? A little past 1, we got this point. Look what corresponds to here. Why do those two correspond? What's this point say right here? Okay, it switches from going up to going down, but we're getting too far. Caden, say it again.
It's just sitting still.
It's not moving, right? What is this y value right here? 0. This says the velocity is 0 at that point, right? Where it crosses the x-axis is a big deal. And what's happening? Yeah, some of you said switching from going up to going down. Well, what's it got to do to switch from going up to going down? It's got to stop. It's got to stop. So at this point, the balloon is stopped. And that corresponds to this. That's kind of interesting because we've already talked about how we're kind of interested in these max and mins like profit or minimum time. And notice how that corresponds to this graph over here, which are the rates. Remember how we've been talking about rates and slopes and stuff, right? It seems like where the rates are 0 seems to correspond to those points. That's a really big connection. And, of course, the idea of rate is slope. So rate and slope are kind of the same thing. So this is 800 right here. Does it seem reasonable that maybe that's what the slope at that blue point is? If that's the rate, isn't rate and slope interchangeable, right? So isn't it reasonable that maybe that's the slope? This slope here is this y value over here? I'll bet it is. What's the slope at that peak? Seems to be flat. That'd be 0. The slope over here. What are the slopes here? Aren't the slopes here negative? And these y values over here are negative, right? Now, again, I'm jumping ahead here a little bit, but I get excited. That's section 4 in chapter 1. We'll get into that. But for right now, I want you to be able to read off of a graph and see what's there. All right, let's go in your book to, we're on page 2. Jump over to page 3. So on page 3, so we talk about functions, okay? So the title of this book is Functions from Symbolic, Numeric, Graphical Points of View. So we're talking about functions. And remember, a function some rule assigns an input to one and only one output. So over here we got a population, the human population. So any 1 year is an input, and assigned to that input is an output. Okay? So we can have tables be functions. We can have equations be functions. We can have graphs be functions. All right? Of course, we know about the whole vertical line test, right? Turn over to page 4. Now, on page 4, we have another function. It's the K function at the top of the page. It is a graph. It is a table of values. Okay, so if I asked you on the quiz, and I may ask you a question like this on the quiz, I may say, what is K of -3? Now, I hope this would be a very easy question. Some people struggle. If people struggle on the first quizzes, sometimes they try to make things too hard, right? We're just trying to understand function notation, right? And so if I give you this and I say, what's K of -3, what are you going to say? You're going to say -4, right? And if I say, what's K of 2, you're going to say, what? 8. And if I say solve for x, this will feel weird for a second, but solve for x, solve this equation for x. What would you say? X equals 4, right? What I'm saying is, when does the function output equal -2? Oh, at an x value of 4, right? So I could ask those either way, and that's what you do when you solve an equation. If I give you a quadratic equals 7, I'm saying, when does this function have an output of 7? I'm asking for one input. There could be more than one input, right? Because you can have several inputs all give you the same output. That's okay. You just can't have one input give you multiple outputs, right? That can't happen. But you can have several inputs all give you the same, right? -2 squared is 4, 2 squared is 4. -2 and 2 both give an output of 4. That's fine. That's still a function, right? All right. Now, here's the weird one, though. What if I ask you, what is K of 7? I ask you on the quiz, what's K of 7? What would you answer? Huh? Why? Okay, you're looking at the y values, weren't you? Yeah, that's our input value. That's our x value. Okay, what would you say? Well, just throw something out there. That's a weird one. You have never been asked this for, so don't worry about being wrong here. What would you say? Dumb question. Dumb question, Mr. Clark. I don't get it. What do you think? Where'd you get that?
Well, because are any answer other than the ones, the -1 and the positive 1 and 0?
Yeah.
It's like not everything's
Oh, so you're looking for a pattern, right? So you're looking for a pattern for this function. Perfectly reasonable thing to do. Absolutely. That's called extrapolating. Interpolating is kind of what you did. Interpolating is where you look at values in between and try to figure out what the missing ones would be. Extrapolating is going outside the data and it's kind of saying, what's the pattern? If it continued, here's what it would be. Okay. Well, actually, and good thoughts, but not quite right. Let me show you this. Let me give you one that's a little more familiar. Okay. So what if I gave you that function as said, what's f of 0? Undefined. Undefined. Okay, now we're a little more confident on that one. Not everybody, but many of you were saying undefined. Now, why you say undefined? Okay, now, technically, the reason yes, technically, 1 divided by 0 is undefined. That's right. We don't have a value for that. The reason the function is undefined at f of 0 is because, and this is the new part here, is because that what we're trying to do is put an input of 0 in, and in this function, is there a matching output for an input of 0? No, because 1 divided by 0 is not a number. 1 divided by 0 is not a number. So that means when I put in a 0, there is no output that goes with it. The function rule does not attach an output to an input of 0. So now I ask again, for that K function, What is K of 7? Undefined. For that K function, there is no output assigned to an input of 7. The K function is defined by that table. The K function is defined by that table. So the K function only has outputs for those whatever 8 values. So any other inputs are not there. Now, if you had an equation, okay, if you had an equation and then you took say a sample of, made a table that was a sample of some of the points in that function, then the table wouldn't be everything because you have this equation, so there'd be others. But this is all we got here. All we know about the K function is this right here. So any other points, we would say it's undefined. Make sense? Okay. So function is defined for certain inputs, and of course that's the domain. So if I ask you what's the domain of the K function, what would you write down? -3, -2, -1, 0, right? You would just write them down. That is the domain. And the range would be the output values, right? That's what it would be. All right. Very good. So, last thing here, then I want to let you work, so let's hustle here. So, this picture on number 4. Okay, one of you guys had talked about piecewise functions being something that might bother you, okay? We want to be able to write a piecewise function, okay, of a graph. On the next quiz, on our first quiz, you will have to do this. Okay, well, piecewise functions are not hard to write, and the only type of graphs I'm going to give you to write are going to be lines and maybe parts of circles. Okay, so those are 2 things we're going to have to know. So we're going to have to know that a line equation is this. Now, we've already been working on that. Okay, we know this is a line equation right here. And then you're going to have to remember this. If you don't remember, I'm going to give it to you right now. This is a circle equation right here. Okay, so you need those 2 things. You're going to need to know those 2 things for the next quiz. Line and a circle. Now, we're going to do one together here. You're going to have one on your homework, and then I'll remind you of this before next Thursday. But guarantee that this is going to be on the quiz. You're going to have a picture, something like this, and you're going to write the equation. Okay? Now, piecewise functions are not that hard. We simply take the pieces, that's why it's called piecewise, and we write the equation for each of the pieces. Now, along with that, we have to give it the domain for that piece. Like this piece only goes from -5 to -3. This piece goes from -3 to 1. This piece goes from 1 to 3, and this piece goes from 3 to 5. So we have to put both of those 2 things together. Now, this is already our y equals right here. So we already have the y equals part of this. Okay? So the problem is going to be for our circle, we're going to have to solve that for y. Okay, when we plug our numbers into it. But this one's already y equals. So let's do the lines first because those are easy. So this line, what do we need? Well, we need its slope. What's its slope? -3/2. So I already got my y equals, so I'll put -3/2, parentheses, x minus, now I need a point. Let's do this point right here. That's easy. -3, 0. So x, so that turned into +3, parentheses, +0. So there, you don't need the +0, but I'll put it for effect so we understand it. That's plus my y point. Okay, so I just picked a point, plugged it in there, and got my slope. Now I'm going to put a comma, and then I'm going to say that goes from -5 to -3. That's how we do a piecewise function. We just write the equation of each piece, and then over here we write down what the domain is for just that piece. Okay, the x values. Now let's skip the circle. We'll come back and stick that in here in a minute. So let's go over to this piece. So what's the slope of that line? 1. We already got our y equals over here, so y equals 1. And then x minus, let's use this point right here, that'd be 1, 0. So x minus 1 plus 0. And then that goes from 1 to 3. Now notice I included those. Now you don't want to include them in more than one. So my line went from -5 to -3, and this one goes from 1 to 3. So when I do my circle, I won't include those there. Okay? When they overlap like that, you just have your choice. You can include in either one. Don't include it in both. Now sometimes you get a piecewise function where one graph goes up here and has an open circle, and then the next graph starts off like that. So then obviously when you do this piece, you won't include this endpoint. and then you will include that endpoint. So sometimes you get situations where the graph's kind of broken, and then you just deal with it that way. Okay? All right, and then what's this line? What's the slope of this line? -1. And then what do we got here? We got the 0.50, so we use that. So x minus 5 plus 0. And then that goes from 3 open to 5, and then close 5. Right? So 3 open because we used the 3 on that other piece, and then it goes from 3 to 5 there. So that's easy, right? So lines are easy. You just got to get the slope, get a point, plug it into that thing right there. Don't even have to simplify it. Okay, now we need the circle. Okay, so this is the center. H and K is the center, and then this is the radius. So I think my center would be here, which is -1, 0. So I'm going to go x minus -1, so x plus 1 squared, plus y minus 0. Now you might think that's silly to put y minus 0, but on the quiz I might give you one where that's a 2. That might be a 2 there, so I want you to see how we would deal with it if it was y minus 2. So let's just pretend that 0 was something else, and so we'll keep it in there. And then equals what? What's the radius? The radius is 2, so 2 squared would be 4. Before we can stick that into our piecewise function, though, we've got to get y equals. We've got to get it in y equals. So, pretty easy. We just subtract that quantity over. No need to FOIL these out. Don't FOIL them out. That'd just be a big pain. We're just going to go 4 minus that quantity. And then, now what would we do? Square root both sides. Now, don't forget, when you square root, you have to do plus or minus. Now, here's the thing. Let's talk about a circle for a minute. Is this graph a full circle? No. If it was a full circle, it wouldn't be a function, would it? It would fail the vertical line test, right? It wouldn't be a function. What we have is the bottom half of the circle. Well, that's what the plus minus is. The plus is the top half of the circle. The minus is the bottom half of the circle. Which do we want? We want the bottom half of the circle. So we're going to erase the plus, and we're going to keep the minus there. Okay? So we're going to have the minus square root because it's the bottom half of the circle. Now, what if this was only a quarter of the circle? What if it was only the bottom quarter here? Well, would that change the negative here? How would we deal if it was only this quarter circle? That'd be our domain. That'd be our domain would take care of that, right? We just say, oh, it only goes from here to here, right? It's still the bottom part of the circle, so it still would have the negative on the square root, right? So if it's the bottom part, you can't ever have part of the bottom and part of the top because it would fail the vertical line test, right? So you're either going to have the bottom or the top. Okay, and again, what if this was y minus 2? See, it's y minus 0, so we're done, really. But if this is y minus 2, we do what? Add 2 over to the other side. So we're going to get y equals 0 minus the square root of 4 minus x plus 1 squared. Okay, so that's why I wanted to put that 0 in there. So 0 minus the square root. I wouldn't have to have it, though. Okay, but if it was a 2 or something else, we would. Okay, so there you go. And then that goes from what to what? -3 to 1, both open, because I already used it. You know, probably if I did these in order, I would have said I'd have closed -3, I'd have probably left this open and closed 1, then I'd have left this open and closed 3. But it doesn't matter. It doesn't matter. As long as you just don't double up on it. Okay. So that's something that will be on the next quiz. You have a homework problem like it, so you can practice it a little bit. So just dealing with circle equations, because those we run into from time to time. The line equation part should be easy. That's how you do a piecewise function. Just write the y equals, and that's already here for you. And then you need the domain part. Okay, on your assignment sheet now, 1.1 homework. You do the 1.1 homework questions. Everybody have one of those assignment sheets? Right? It's got the assignments on it. So 1.1 for Monday, and then don't forget that calculator thing. Calculator scavenger hunt sheet for Monday as well. All right, rest of the time to work. Answer books up here if you want to check anything before you go.